that, we need to talk about Dalton's law of partial pressures. This might be obvious or not, but hopefully as we go along it becomes more obvious to you. In a mixture of gases, if we had a container, so here's a container, and if we had two gases inside this container here, we have a lid on it here. It says in a mixture of gases, the total gas pressure, so the total pressure inside of this container is equal to the individual pressures of each gas. So if I had oxygen in here, I'd figure out the pressure of the oxygen. And if I had nitrogen in here as well, I'd figure out the pressure of the nitrogen. And I'd add those two together to give me the total pressure inside this container. Okay? So the total pressure is equal to the individual pressures, for example, oxygen, and the pressure of the nitrogen. So let's say, for example, the oxygen pressure is 100 kilopascals, and the nitrogen pressure is 200 kilopascals. Well, if I have oxygen gas in here at a pressure of 100, and I have nitrogen gas in here at a pressure of 200, the total pressure inside this container is 300. Yes? Okay? In case we're stating the obvious. Okay? So if I have one gas that exerts 100 and the other one exerts 200, the total pressure inside here is 300. Okay? That's Dalton's law of partial pressure. Okay? This is one of those laws where, had I been alive a little bit earlier in my life, I totally would have claimed it, because even I could come up with this one. Okay? Like, you don't have to be overly smart to get this one, right? But anyway, having said that, there's more to it than that, okay? However, but that's the basic general idea, okay? So the total pressure is equal to the individual pressures inside of that container, all added together, okay? We're going to look at this one as we do the example, so don't let me forget about this, but basically it says the greater the amount of a gas that you have, remember, amount refers to moles, yes? Or N. The more amount or moles of a gas you have, the more pressure it exerts. And I'll show you that coming up here in our first example. Okay? The greater its contribution to the total overall pressure. All right? Unfortunately, guys, and I gave you the notes, so don't complain. But nonetheless, you don't have a lot of room to do this example with. So if you want to do it on a different piece of paper, that's fine. This is a double-sided one, so you'd have to find somewhere else to do it. If you want to squeeze it in there and you think you can, good for you. I don't think I could, but good for you. So we need to look at, once again, ideal gas law for these questions. We're going to have masses of gases, so mass of gas. We're going to be talking about the pressure and the volume and the temperature and R and all those things. So we're going to look at ideal gas law. The only difference today is we might have to use the ideal gas law more than once. In other words, we're going to have to do it for each individual gas here. So what I like to do is I like to set up a little table here. Okay? So I know I have a 10-liter tank that holds 50 grams of nitrogen gas. And I also have some carbon dioxide gas. Okay? So I would set it up something like that there. And you don't have to set up a table by any means. If you want to do all this stuff for one gas and all the other stuff for the other gas, that's fine. I think the table helps, especially in certain questions, but it's 100% up to you. I don't care. Okay? When we talk about gases, we talk about the usual, P, V, N, R, T. And of course, the other form that we know is N equals little m over big M. So I'd probably include that here just in case. Okay? So that kind of stuff there. I'll move it up here a bit. Okay? You guys have the question in front of you there as well. So those are kind of those are the main variables that we talked about yesterday, and we'll talk about again today. Okay? So let's take a look at some of the information we have here. By the way, what are we looking for in this question? It says calculate the partial pressure of each gas. Calculate the partial pressure of each gas. So really that's what we're looking for. It says partial pressure, and you know what? All they mean is calculate the pressure of the nitrogen gas, calculate the pressure of the carbon dioxide gas, and of course if you add those two together, that's the total pressure inside this tank here. Okay? Calculate the partial pressure of each gas and the total pressure, which, by the way, the total pressure is simply the two added together, right? The pressure of the nitrogen gas and the pressure of the carbon dioxide gas. Those are the things that we are looking for in this question, okay? Guess what? I'm pretty sure we have all the other stuff that we need here, okay? Otherwise, we wouldn't be able to do the question, right? And you can always do the question. So let's take a look here. We have a 10-liter tank. That's the first thing I see here. So picture this. Okay, this goes back to Unit 1. If you haven't been reviewing yet, you probably should start. Okay, here's 10-liter tank. 10 liters of gas fits in here, amazingly. I know it looks small, but it's not. 10-liter tank, okay? Inside of here, I'm going to put some nitrogen gas and some carbon dioxide gas. Let's focus on the nitrogen gas first. Nitrogen gas is inside this 10-liter tank. What is the volume of nitrogen gas that I have? 10 liters. Why? Always takes the volume of the container, right? Gases always fill the volume of their container, yes? That's like properties of gases less than 1 or 2 or 3. 3, maybe. That's one of the properties. Gases always take on the shape of the container. If this is a 10-liter tank, nitrogen will take on the volume of 10 liters. Okay? Well, let's switch gears now. Now I have some carbon dioxide in here. Is there nitrogen in here? Sure there is. How much volume is the carbon dioxide gas going to occupy in here? Once again, 10 liters. Okay? The carbon dioxide gas also takes on the shape of the container, right? Remember, mostly empty space in between them, so they're both going to have the same volume, okay? Both of those gases are going to take on the shape of this container here, and I know there's two of them there, I get that. But remember, there's a lot of empty space in between gases as well. So they're going to take on the shape of their container. In this case, they both have a volume of 10 liters. They take on the shape of the container. They fill it up, okay? We've got 50 grams of nitrogen. I can put that here. And of course, 50 grams of nitrogen, or sorry, carbon dioxide as well. 50 grams and 50 grams. The gas is at 20 degrees Celsius. So most of you guys would probably put this in here. But remember, listen, if both of these gases are in the same container, and the container is at 20 degrees Celsius, or the gases are at 20 degrees Celsius, guess what? They probably both have the same temperature, yes? They're in the same container. You can't have two gases with different temperatures unless you're mixing them together. If they're in the same container, they have to have the same temperature, okay? So this also is 293.15 Kelvin. Both gases are in the same container. The container's at 20 degrees Celsius. Both gases are at 20 degrees Celsius, okay? R we know is 8.314. And guess what? I also know big M for both of these because I know the molar mass for both of these. I can look them up on the periodic table. Nitrogen's 14.01 times 2, which is 28.02 grams per mole. And carbon dioxide is 32 and 12 is 44.01 grams per mole. Okay? So look what's left. What do you have left to solve for here? Well, geez, I need to solve for the pressure, right? In order to do the pressure, if you don't know what formula we're going to use this formula here. Pressure equals nRT over V, yes? PV equals nRT, divide both sides by V, right? So if I'm looking for the pressure, I need to know nRT and V. I don't know N right now, but guess what? These two would give me N, correct? Mass over molar mass, right? N equals little m over big M. So mass, molar mass would give me N here, so I can do that. Which works out to be, I believe, 50 divided by 28.02, about 1.78. Actually, I'm going to use a different color here. 1.78 moles. Don't take that off your calculator. make sure you keep that on your calculator. And I'm going to find the pressure now. So I'm going to go N times R times T divided by V. And I get a total of, I'm going to move this down here. Pressure of nitrogen here is 434.9124019 kPa. There's a reason I wrote out the whole number, which I'll explain in a second here. Okay, so that is the pressure of the nitrogen. Significant digits, rounding, etc., we'd say 435 kPa. Okay, all said and done. 435 kPa. All right. We'll do the same with carbon dioxide. So we'll do it the same with the other side here. So once again, that's okay. I'm going to figure out these two here to give me N, right? Mass and molar mass. So 50 divided by 44.01. I get about 1.136 moles. I'm going to take that, once again, times 8.314 times temperature, 293.15, divided by the volume, which is 10. And I get about, here, pressure of carbon dioxide is 276.897, etc., kPa, or 277 kPa. Final answer. Okay. Good so far? All right. We have our two partial pressures, or pressure of each gas, yeah? We have this pressure here. This is the pressure that the nitrogen exerts. This is the pressure of the carbon dioxide, okay? Now, I also need to, that basically answers this part right here, right? Partial pressure of each gas, and now the total pressure I need to do as well. Well, the total pressure is equal to those individual pressures at the bottom here, right? 435 and 277. But don't take those two numbers, because this is rounded and that's rounded. We need to take this one and this one, of course, yes? We need to add those two together. So, we need to take here the unrounded numbers. Now, to get this unrounded number here, if you didn't write this all down, and this quite often happens with partial pressures, if you don't write this whole number down, you'll have to go back and do the calculation over again, right from scratch, because this won't be on your calculator anymore unless you know how to recall it, and I don't. Okay? Yeah. Okay. You need to take this number, and I don't know if that's possible, but you need to take this number and add on to this unrounded number here. Okay? This one's still in my calculator because this was the last one I did. This one's not, or at least maybe it is. I don't know. I don't know how to do it. So I'm not sure if you can add those two together. I don't care. But I always just take this and then that there. So that one's still my calculator.
Interruption. We now need any grade 11 last name starting with N through Z.
Adding these two together, okay, I get this number here, 711.8095957. Okay? I need to round that appropriately now to, of course, 712 kPa. Now, you might say I get that number regardless of what number I take here, and the answer is, in this case, yes. Not all the time. You could technically be off by one. Okay? So you need to make sure you take the unrounded numbers and then round that. Okay? So don't forget that part. Okay? That's Dalton's law of partial pressures. Basically, PV equals nRT twice. Okay? Find the pressure of each one, add them together. And then, of course, we can do other stuff like the next example here. Before we move on to the next example, I want to show you something. Look, earlier we took there was that note that said the greater amount of a gas, the more the pressure. So look, I want to explain something to you because we're gonna do this again with molar volume. It's kind of the same thing. But look, 1.78 moles of a gas, 1.13 moles of gas, right? So 1.7 compared to 1.1, right? Look at the pressures. The more the amount, the greater the pressure. Make sense? Why? Less moles, less pressure. Why does that make sense? Yeah. Yeah, no. You're close. I don't know if you're quite saying it right. No, no. More moles is what? Ultimately, more moles means more what? Sorry, what? More gas, more collisions. Because more moles means more molecules, right? 1 mole is 6.02 times 10 to the 23 molecules. 1.7 would be more. 1.1 would be less, yes? So more molecules of gas here, right? Less molecules here. The more molecules you have, the more collisions you have. The more collisions you have, the more pressure you have. Okay? Does that make sense? Sure it does. They're in the same container, same temperature, same volume. Okay, look. I'll even show you one extra thing here. This is important. Oh, not that. Think about this. When you think of this formula, guys, and we're going to look at this coming up here. When you think of this formula, and you think about two gases, right? Look, what's the same between the gases? The temperature is going to stay the same. R is going to stay the same. Volume stays the same. What does that mean? What's the relationship between, what can only change between these things? The only thing that changes between the problem that we just did was this, which totally affects that, right? The more moles you have, the more pressure you have. Simple, right? Those are the only two things that really matter because everything else is the same. The temperature stays the same, the volume stays, R is the same. The only two things that can change are P and V. The more N you have, the more moles, the more molecules, the more collisions equals the more pressure. Yes? Okay? So that has to hold true for these types of questions here. So let's not forget that. Okay? Oh, I messed that up there. But that's all staying the same. So really P and N are the only things that really matter. Okay? So the more amount of a gas you have, the more pressure you're going to have. In fact, you could even get crazy. Look at this. You might want to consider this sometime down the road, not Monday because that's too early. I don't think that's going to happen. I'm almost positive. But someday down the road, you could even go as far as to say this. Because if you're saying that all this stuff doesn't really matter except P and N, then look, if I had 1 mole of gas and it exerts, let's say 100 kilopascals of pressure. If I had 2 moles of gas in that container, so if I had twice the amount of gas, I could pretty much guarantee you it would exert 200 kilopascals, twice as much, right? If I had a half a mole of gas in that container, it would be 50, right? Because the more gas you have, the more pressure has to be. And it's a direct relationship. It's like a perfect direct relationship, okay? So the more moles you have, directly proportional to the pressure, etc. Okay? If you had 50 here, well, you'd have 50 moles of gas, well, it'd be 50 times as much, so 50, 100, or 5,000 as we'd say. Okay? Directly proportional. More gas you have, the more pressure you have. You can go back, if you don't believe me, and you can find a common relationship between 1.136 and 277, 1.78 and 434. There's the same number. If you look at that, the same factor there. There is. Okay? All right, moving on here. One more example, and then we're going to do a little bit something different here, and then I'll give you some time to work. This one here, let's get this one set up here. Fluorine gas and chlorine gas. So for me, chlorine gas, chlorine gas, chlorine gas. Okay. Once again, probably a very good chance we're looking at partial pressure stuff here. So guess what? PV, nRT, and little m and big M probably as well. Start looking through the question here. What do I know? I got a 12-liter tank. Well, that probably could be the volume for each gas here, 12 liters. 12 liters. Okay. R, might as well fill that at 8.314. 8.314. Temperature, I see 17.8 there. Says that's the temperature. The tank has an internal pressure of that with a temperature of 17.8, so 17.8. And 273.15 is 290.95. And guess what? If it's that, it's also that. Okay. Now, so we've taken care of this here. That's gone. That's done. Now we got to look at the rest of this. The total internal pressure. So the total internal pressure, the total pressure of this tank is 1,500. That's the total pressure. The chlorine gas pressure, the partial pressure of the chlorine is 450. Okay? So that would go there. So since we know that's 450, we know the total pressure of the tank is 1,500, I guess that leaves about, what? 1050 here, yes? Because this and this, I shouldn't do that because it's going to look like I put decimals there. This and this gives you 1,500, yes? Do it on the calculator, 1050 and 450, 1,500. That's the total pressure. So those two gases have to add up to the total. So there you go. Look what you already have. Right away when I look at this, I say PVRT. Guess what? I can probably find N. Yeah? Right away. So once again, you could do that now. You can do it later. You can fill in a few more things if you want to. F2 is 38 grams per mole. And Cl2 is 70.90 grams per mole. So either way, at some point in time, look, we have PV, we have R and T. The only letter we're missing is N. So we could probably solve for that in both cases. Okay? By the way, look, stop for a second. Listen. PV, nRT. Once again, just looking at this relationship, which we're going to talk more about. N and N. What do you know about these N's right now just by looking at this question? Absolutely. Less, right? Has to be, because look, the pressure's 1050. I got to have more of this gas than I do of this gas because that's only 450. Yeah? Direct relationship. Okay? So I don't know what that number is yet, but we're going to find it out. Okay? Because everything else is the same. So it has to be. All right? So here we go. To find N, by the way, I'm taking a few shortcuts. So if you need to sit down and say, I don't know how to get N by itself, then you need to go PV equals nRT, divide by RT, divide by RT, N equals PV over RT. I've done this a few times, and I'm trying to save a little bit of time. There's nothing wrong with that. Do that. I don't care. Take as much time as you need, but you need to come up with this. Okay? Solving for N. That's what we're going to do here. All right? So N, let's see here. We're going to take P and V. That's 12. Don't forget brackets on the bottom, right here, right? Brackets. 8.314 and 290.95. This works out to be 5.208, etc. Okay? Actually, you know what? I got to finish this question right now because I have that number on my calculator. I don't want to come back and do all that stuff. So I better take this now. I know N. And remember, that stuff all ties together as well, right? N equals little m over big M. So N equals little m over big M. Mass is N times big M. Yes? I have N on my calculator. That was 38. So this is at 5.20 and 38. And if I multiply those two, I get 197.936 grams. And then we have to talk about significant digits, of course. Calculate the mass of each gas was this question, yes? So, once again, if I look at significant digits, if you go back through, there will be 3 of them. So that would be my final answer for this one. Okay? Good? 198 grams. Mass of each gas. So that's that side there. Other side, let's see. 450 and 12 divided by 8.314 and 290.95. And that is about 2.23. Okay? So, we're right, yeah? Right? When we said the amount has to be bigger. Makes sense. That and that combined to give you that there. Okay, if I multiply those two numbers, mass is equal to N times big M, yes? So I multiply N and big M, and it's 158. And once again, I'm just going to leave it like that, 158 grams all around it. It's 158.27 something, 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 or 158 grams, 3 significant digits. Okay? Good? Okay, questions, anyone? Questions? All you're doing today is, once again, PV equals nRT, and N equals little m over big M. Same thing as we did yesterday, you just got to do it, in some cases, twice. If you don't know what this, like, for example, if you have to solve for the volume for each of these or something like that, or the volume or something like that, if you can't do this kind of thing, that's okay. You got to write stuff out and figure it out, yes? Take your time, make sure you know what formula you're using, and figure that out, all right? Tomorrow we're going to go to the lab and we're going to collect gas. And one of the safest ways to do this, to collect gas, is using what we call the downwards displacement of water. And there's going to be a picture there for you as well. Yeah. Actually, this is on the first page, right? On the bottom there. Okay. So this is still on the first page at the bottom, sorry. Use downwards displacement of water, okay? And I'll show you what that looks like in a bit here. You take a graduated cylinder, you can fill it with water and invert it. So you're going to take a cylinder, okay? I haven't decided which one we're going to use yet. We can use, there's a couple options. A graduated cylinder, which you guys probably have used before, or we can use a gas cylinder specifically meant for that, which is a long skinny tube. It's got a closed end on one end, and the other side's open. We're going to fill it with water. We're going to cover it with our hand or with our thumb. We're going to flip it over, and we're going to put it underneath the water. And what happens, of course, is the two pressures are equalized to each other. And what happens is, of course, no water leaks out. Okay? You still got a tube. It's like you guys have done before with something, but the water's all still in there. Okay, inside that tube. Okay. The one thing you have to be careful of, and I will demonstrate all this tomorrow, so just relax, but you do need to copy down a few things. One thing you want to look for is any air bubbles that do get trapped in there, because air bubbles take up a volume, okay? We don't want air bubbles. We just want the volume of the gas that we're releasing tomorrow. Air is a gas. We don't want that volume, okay? We don't want to start off with some volume in there already. So that's one of the things we have to be careful of. I'll show you what to do about that tomorrow, okay? The gas will travel through the water and collect at the closed end. So if this is in water and your hands are underneath the water, we're going to let gas go, and it's going to go up this cylinder, and it's going to collect at the top part and start pushing water out the bottom. Downwards displacement of the water, which is downwards pushing out the water, basically. Okay? The gas is going to get trapped above the water. So you're going to see, I'll show you what you're going to see here in a bit. The gas pushes the water down and out of the cylinder, leaving the gas trapped above the water. This here, I'll explain on the next one. This is important. Okay, oops, we don't need that. Okay. Now, look at all the things you can get from this experiment tomorrow. And this is what I want you to focus on for right now. You can get the volume of the gas from the cylinder. So we can get the volume of the gas. The volume of the gas that we released. Good, perfect. We can get the pressure of the gas from what we call a barometer. You guys know what a barometer is? Back in the old day, we had one in our house. It's a barometer. And all it does is measure air pressure. But only they don't measure the pressure. They don't actually have numbers. They just had a dial. And the dial would push either way. And if it went one way, it'd be nice and sunny. And if it went down, it'd be nice and cloudy, probably rain. You could predict the weather just by the changing pressure. That's what the weathermen do. Not very successfully, usually. Anyway, so you can get the pressure from the barometer. There is a barometer in the room and measures pressure. Okay? And you can get the temperature. We're going to use a thermometer. How about that? We can find T, thermometer. Look what you have up there, PVT. What else do you know? R. What else can you find? N. Sure. You can find N. Right? What does N turn out to be? That's part of the experiment. Okay, so we're going to use those calculations to find N. Okay, that's what you're going to get from the gas cylinder and the pressure and all that other stuff. However, we need to do more with that. My question to you tomorrow is going to be, what is the molar mass of the gas that we are collecting? Okay? What is big M? What is the molar mass? If I want to find the molar mass of the gas, what else do I need to know? I can find N from those. What else do I need to know? The mass, little m, right? The mass of the gas. How much gas did I release? The mass. Well, how am I going to figure that out? Because can you just take the gas out and weigh it, put it on the scale after you're done? No. How am I going to weigh the gas that's trapped above the water? That's going to be pretty tough. So what we're going to do is we're going to weigh the gas. We're going to use a Bic lighter tomorrow. We're going to weigh it before, and we're going to weigh it after. And that way, when we weigh it before, let's say it weighs 20 grams. We weigh it after we're done this experiment, it weighs 19. We have 1 gram of gas that we released and collected. Okay? So we're going to take the mass before, subtract the mass after, is how we're going to get the mass of the gas that we've released. Okay? So that'll give us the mass. We'll have N. We can calculate the molar mass. Okay? And if you do this very carefully, it's very accurate. True. Okay? One thing you want to listen carefully to, well, a couple things. First of all, make sure you use the right units. Yes? We know what these units are, or they should be. right? PV equals nRT. We know the units to go in there. We just did a whole worksheet on them, for crying out loud. Make sure when you do your measurements tomorrow, they're in the right units. Hint, hint. Okay. Secondly, this is kind of what the system is going to look like. This is on the back side, of course. Not quite the same. We don't have this gas generator. We're just going to have a Bic lighter sitting down here, and we're going to let gas go up like so. Okay? So yes, it's going to be underwater. Okay? You're going to get your hands wet. I'm telling you. So if you don't want to wear the long sleeves tomorrow, or you want to roll them up, that's fine. Okay? It's going to travel to the top, and gas is going to start to collect here. Meanwhile, the water's being pushed out the bottom. You won't see that, but the water's being pushed out the bottom. Here's something else. Make sure that when you get done, and I will do this again for you tomorrow, that has to match up with this, aka the volume of this gas has to match up with the water level inside of this sink. Okay? We're actually going to use a sink tomorrow. And the gas volume has to equal the sink volume. In other words, you should be able to basically draw a line straight across there when you put that cylinder flat on the sink. And the reason you have to do that is simply this. We talked about equilibrium, right? Pressure outside equals the pressure inside. When those two match up, the pressure outside of here, by the way, this is the room pressure, aka barometer. Okay? If we want to use that room pressure from the barometer, those two levels have to match up. If we don't want to do that, then you need another different gauge to measure room pressure. That's going to be tough. I don't have one for you. Okay? Or to measure that gas pressure, I mean. So this outside pressure will equal the pressure inside the gas here if those two line up. Equilibrium thing. Okay? All right? So those have to match up. Okay? Then there's one more thing, and that's why we talked about Dalton's law of partial pressures. To get your actual best answer, you need to take this into account. Otherwise, you're going to be off, probably. So to get the right answer, okay, we need to adjust something here. Okay? When you, by the way, this is what happens. When you put the Bic lighter here and you start releasing gas up, right? So it's going up and up and up. Guess what? You're not only collecting gas from the lighter going up to the top and getting collected, but inside water, there's actually water gas. Inside liquid water, there is some gas molecules inside of there, no matter kind of what temperature you're at, okay? And I'll kind of go through that with you. But there is some water molecules of gas that have not hooked up to make liquid, okay? They're independent, they're their own gas molecules. So guess what happens? They're also going to travel upwards here, and they're going to collect up here. So what you are collecting up here is a mixture of, well, the Bic lighter, I'll just call it Bic gas, and you're also going to get some water gas up here in this section here, okay? And that's okay, but remember, okay, that just happens. Think about it this way. If you had gas that's at if you had water that's at 5 degrees Celsius, okay, that's cool, right? Fairly cool. You're probably not going to have a lot of free molecules floating around because there's not a lot of energy for those molecules of gas, right? Remember we talked about that before. Temperature is lower, so less movement, a lot more hooked up, yes? Okay? Compare that to a gas that has a temperature, or compare that to water that has a temperature of, let's say, 98 degrees Celsius, almost boiling. Is there going to be a lot of gas in there trying to almost escape? There's going to be a ton of gas in there, right? We're almost at 100, it turns all into gas, yes? You're going to get a lot of pressure from the gas because at 100 you got a lot of steam, right? All gas molecules. At 98, you're going to have a little bit less. At 50, you're going to have less. At 40, you're going to have less. 30 less, 20 less, 10 less, 5 less. 0, probably not a lot. Probably because it's in solid form, theoretically speaking, yes? Because there would be no more liquid, and now it would be a solid. You wouldn't have to worry about the gas part, okay? So, what we need to think about here is, what's the temperature of this water? How much of this gas we collected here is actually water? And we need to take that out of the equation. And to do that, you don't have this yet. I'm going to give this to you right away. But you can just make a note somewhere on here. Here's a list of temperatures of water. So this is the temperature of water. And the corresponding pressure that that water would exert. Okay? So let's say we had gas at 20 degrees Celsius tomorrow in our sink. You're going to put the thermometer in, you're going to measure it. Out of the entire pressure that I've collected at the top, I'd expect to have 2.33 kilopascals of water pressure that I don't want as part of that. The formula is this right here. Here's what you're going to do. The total pressure is equal to the pressure of the gas plus the pressure of the water. I just want this one here. Pressure, well, this is the big lighter thing. Okay? I just want that by itself. So what are you going to do tomorrow? You will take, to find that actual pressure, and we'll talk about this again tomorrow, you're going to take the total pressure of the room, the barometer, room pressure, barometer, and you're going to subtract the pressure of the water. That there. Okay? So if you are doing this experiment at 20 degrees Celsius tomorrow, the one I circled there, you would take the total pressure of the room. By the way, the pressure of the room is going to be about 102-ish tomorrow, roughly, give or take a little bit. 102. You'd take 102 and you'd subtract the 2.33, and you'd actually end up with about 99.6 or something like that kPa of pressure of gas. Okay? And that's what you're going to use in PV equals nRT. That's the pressure you need to use. Okay? So, that's the last little tricky part about this. And then, of course, I will help you with this. This is your first lab. So I need to lay everything out for you. We need time for that. So the fact that we're probably going to have our test on Monday is not likely at all. I don't know why I just don't change it now. Wednesday, even that, I'm not going to lie to you, is probably a bit optimistic because I want to make sure you guys have some practice. We probably should have a quiz on PV equals nRT, which we'll probably have on Friday. So, yeah, I don't even know if Wednesday's possible. Then Thursday's Halloween. That might be a possibility, although I kind of hate to do that because I know some of you guys are going to work on costumes forever.